Imagine you have dreamed your entire life of jumping into a black hole. You've read Hawking, studied Kip Thorne, watched every movie, and you still wonder what is really inside. At the heart of our Milky Way lurks a supermassive black hole called Sagittarius A star. One day, against all odds, you finally go there. Your spacecraft stops at a safe distance. You leave the airlock and begin to fall. There is a 6-letter word that best describes what will happen to you: crush. Your descent will last about an hour and will end in death. Your ship will remain in orbit, watching your final journey. But even before the fall truly begins, you face your first problem. The gravity of Sagittarius A star is overwhelming. Its mass is millions of times greater than that of the Sun. This immense pull captures stars and gas, forming a thick, glowing disk of plasma spinning around the black hole at nearly the speed of light. Friction inside this disk heats it to billions of degrees. It erupts with ultraviolet, X-ray, and gamma radiation, powerful enough to blind you instantly and burn you alive. So let's imagine you're wearing an impossibly strong spacesuit. It shields you from the heat and filters the deadly radiation. Even so, the disk is blindingly bright. Your helmet uses a special visor that dims the light, allowing you to finally see. The first thing you notice is its color. The disk glows blue. Your visor passes only visible light, and in this range, the disk shines mostly blue, just like the hottest stars in the universe. But something else feels strange. One side of the disk is brighter than the other. This is the Doppler effect, the same phenomenon you hear when a speeding car changes pitch as it passes you. The plasma is moving so fast that the side rotating toward you compresses its light, shifting it to higher energy. The side moving away stretches the light, making it dimmer. You are no longer just falling into darkness. You are falling into a cosmic furnace, a place where space itself is being torn apart. As you watch the black hole, something feels deeply wrong. The far side of the glowing disk appears bent, stretched around the event horizon, forming a distorted ring of light. This is the power of gravity itself bending light, an effect known as gravitational lensing. Looking in one direction, you are actually seeing matter located somewhere else in space. The background stars appear slightly blue. You don't feel it, but time is slowing down for you. Your clock is ticking more slowly than the clocks of distant stars. Their light reaches you compressed in time, shifted toward higher frequencies, giving the stars a faint bluish hue. Your fall through the disk feels strange. During the first 10 minutes, the black hole seems to drift away from you, even though you are clearly falling toward it. This optical illusion is caused by aberration. As you accelerate, light from the front of your motion is bent into your forward view, making the black hole appear displaced. After 10 minutes, your speed reaches 4% of the speed of light. Now the black hole begins to grow in your field of vision. Your velocity keeps increasing. Light coming from ahead becomes brighter, while light from behind fades into darkness. This is Doppler shift again. You are chasing the light in front of you, while the light behind you struggles to catch up. Minute by minute, you skim above the blazing disk of matter. Then, after about 57 minutes of falling, the disk simply vanishes. You have reached the region where matter can no longer remain in balance.
Here, gravity becomes so extreme that the plasma can no longer orbit. It twists into a tightening spiral and plunges inward. From now on, everything happens fast. In just 2 minutes, you move twice as close to the event horizon as before. From this region onward, any light coming from the outside world is doomed to fall with you. This is the photon sphere, a place where light itself can orbit the black hole. 24 seconds later, You cross the event horizon. There is no way back. Yet you still see the distant stars falling beside you. You can even see your spacecraft still circling far behind. Its clocks appear slowed, but they are still ticking. Your own body remains visible too, even your feet. Strangely, the black hole does not swallow your entire view. Even now, it fills only about 15% of your field of vision. Everything else is stars. This is caused by extreme aberration of light. Moving at unbelievable speed, light from the sides and even from behind is dragged into your forward view. Your vision compresses in front of you and stretches behind you. The ship behind you looks larger, even as you fall away from it. The next 30 seconds pass in a blur. You wish you had chosen a larger black hole, where you could have survived for hours longer. Then it happens. An overwhelming force grips your body. This is spaghettification. Your head is slightly farther from the black hole's center than your feet, and the difference in gravity is so immense that your body is stretched violently apart. Even your atoms are torn from one another. In your final moments, it feels as if you are falling onto a flat, perfectly black surface surrounded by a glowing ring of light. A fraction of a second later, the crushed remains of your body reach the center. Matter is stretched, time is twisted, and space itself collapses into something no human mind can ever understand. Your journey ends here. Modern physics cannot yet describe what truly happens at the center of a black hole. Our current theories speak of singularities, points where the curvature of space-time becomes infinite. Roger Penrose once said, after receiving the Nobel Prize, "The greatest mystery is the singularity, because we simply don't know what to do with it. Black holes hide singularities from us. As matter collapses inward, its density grows beyond anything imaginable, and we have no idea how to describe the physics at the center. Densities, temperatures, everything there lies far outside the limits of our theories. There is no complete theory for the heart of a black hole. To understand it, we would need to unite quantum mechanics with gravity, and no one yet knows how. But here is the twist. Black holes are not truly black. They are not the eternal prisons they were once thought to be. Some physicists believe that information may escape, perhaps back into our universe or even into another one. Today, many researchers no longer see black holes as cosmic tombs, but as the universe's most powerful telescope and perhaps its ultimate quantum computer. They may be the key to understanding reality itself. Reality, it seems, is stranger than fiction, and nowhere is that more true than in the case of black holes. They are more bizarre than anything science fiction ever imagined, yet they are not fantasy. They are fact. So let's use black holes as a cosmic magnifying glass to understand how space and time can exchange roles, whether bridges between universes might exist, why space itself may not be fundamental, where an infinite number of universes could be hiding, and how you can be burned and spaghettified at the same time. By the end of this video, the pieces will fall into place. You will see why, in the search for a quantum theory of gravity, we may have already glimpsed a deeper layer of reality. This video is based primarily on the book Black Holes: The Key to Understanding the Universe by physicists Brian Cox and Jeff Forshaw. Brian Cox is a true punk physicist. Before becoming a professor at the University of Manchester, he played keyboards in the band D-Ream. Today, he is the Royal Professor for Public Engagement in Science and a Fellow of the Royal Society. His co-author, Jeff Forshaw, is a specialist in quantum chromodynamics, also a professor at Manchester and a recipient of the Maxwell Medal. He is a marathon runner who claims that after the 30th kilometer, his thoughts about particle physics become crystal clear. At the center of our galaxy lies an object with 4 million times the mass of the Sun, a gravity well so deep that even light cannot escape. We call it Sagittarius A star.
Black holes are born where the most massive stars die. They live at the centers of galaxies and at the edge of human understanding. Gravity creates them when enormous amounts of matter are crushed into an impossibly small region of space. The laws of physics predict their existence, but cannot fully describe them. Each black hole is a mystery we have not yet solved. The story begins with Albert Einstein. His theory of relativity predicted two astonishing things. First, massive stars are doomed to collapse into black holes, hiding a singularity inside. Second, our own past contains a singularity, the beginning of space and time itself. We call it the Big Bang. For decades, physicists refused to believe black holes were real. Even Einstein wrote in 1939 that they do not exist in reality. Arthur Eddington was blunt. There should be a law of nature to prevent a star from behaving in such an absurd way. But there is no such law, and the universe did not listen.
And the stars really do behave exactly like that. Today we know that black holes are a natural and inevitable stage in the lives of stars several times more massive than the Sun. Our galaxy contains millions of such stars, and therefore millions of black holes. Stars are gigantic balls of matter fighting their own gravity. They burn hydrogen into helium, creating pressure that resists collapse. Our Sun converts 600 million tons of hydrogen every second, a mountain of fuel, burning steadily for billions of years. The Sun feels enormous. 1 million Earths could fit inside it, but in cosmic terms, it is a dwarf. The largest stars are 1,000 times wider, with diameters approaching 1 billion kilometers. Place one at the center of our solar system, and it would swallow Jupiter. And these giants are doomed. When the fuel runs out, gravity wins. Small stars become white dwarfs, objects the size of Earth but with the mass of the Sun. They are saved by quantum mechanics. Electrons cannot stay still. When compressed, they generate pressure by their frantic motion. In 1930, a 19-year-old physicist named Subrahmanyan Chandrasekhar made a crucial discovery while sailing to England. Electrons cannot move faster than light. If a star is heavier than 1.4 times the mass of the Sun, electron pressure can no longer stop the collapse. The star keeps falling inward. It becomes a neutron star. Electrons and protons merge into neutrons, forming a city-sized sphere heavier than the Sun. Imagine 1 million Earths crushed into a ball the size of Moscow. A teaspoon of this matter weighs 1 billion tons. Some neutron stars spin 700 times per second. The first one, discovered in 1967, pulsed so regularly that astronomers jokingly called it little green men. Gravity on their surface is 100 billion times stronger than on Earth. Anything that falls there is shredded into subatomic soup. But even this has a limit. If the core is heavier than about 3 suns, nothing can stop the collapse. A black hole is born. We don't just predict them, we see them. In 2015, the LIGO detector caught gravitational waves from the collision of 2 black holes 1 billion light-years away. They weighed 29 and 36 times the mass of the Sun and merged in just 0.2 of a second, releasing more energy than all the stars in the visible universe combined. In 2019, the Event Horizon Telescope captured the first image of a black hole in the galaxy M87. It is 6.5 billion times heavier than the Sun. The dark center is its shadow,
and the glowing ring is superheated gas falling inward. Black holes are perfect laboratories for physics. To understand them, we need everything at once: thermodynamics, quantum mechanics, and, above all, Einstein's theory of relativity. Let's begin there. At school, we're taught that gravity is just a force that stops us from jumping too high. Isaac Newton formalized this idea in 1687, and his theory still guides spacecraft today. But Newton made two crucial assumptions. First, time is universal. If you synchronized every clock in the universe, they would all tick at the same rate. Second, space is absolute, a fixed, unmoving stage where reality unfolds. It sounds like common sense, but both ideas are wrong. In 1971, physicists Joseph Hafele and Richard Keating performed a brilliant experiment. They bought airline tickets around the world, along with 4 atomic clocks. They flew once eastward, then westward, and finally compared their clocks with reference clocks at an observatory. The result was shocking. The clocks flown east lost 59 nanoseconds. The clocks flown west gained 273 nanoseconds. Tiny differences, but not zero. And they matched Einstein's predictions perfectly. Time, it turns out, does not flow the same for everyone. It depends on how fast you move. But maybe at least distance is safe. Look at your hand. Who would dare claim that the distance between your fingers depends on your point of view? Einstein did. Space is not what it seems either. The distance between 2 points depends on the observer. This is not philosophy, it is experimental fact. Take the Large Hadron Collider at CERN. To us, its circumference is 27 kilometers, but to protons racing inside it at nearly the speed of light, that same ring is only about 4 meters around. Einstein understood this in 1905, before any of these experiments existed. So what led him to such a radical idea?
Einstein saw a contradiction between Newton's gravity and Maxwell's theory of electromagnetism. Maxwell's equations say something extraordinary. Light always moves at the same speed, about 300 million meters per second, no matter how fast the observer is moving. Imagine an astronaut inside a spaceship throwing a ball forward. To the astronaut, the ball moves at the speed of the throw, but to someone watching from Earth, the ball moves faster because the ship itself is moving. Now try the same experiment with a flashlight. No matter who measures it, on the ship or on Earth, the light travels at exactly the same speed. This is bizarre. There were only 2 ways to explain it. Either Maxwell's equations were wrong, or our ideas about space and time were wrong. Einstein chose to change space and time. If he could have pulled just one idea from thin air that leads directly to the most famous equation in physics, E equals mc squared, it would be this: the space-time interval. The idea is beautifully simple. Return to the spaceship. The astronaut holds 2 flashlights, one pointing forward, the other backward. He switches them on at the same time. From his point of view, the ship is at rest, so the light reaches the front and back of the ship simultaneously. Now look at the same event from Earth. The speed of light is still the same in both directions, but the ship is moving forward, so the backward-moving beam hits the rear of the ship first, while the forward beam must chase the moving nose. From Earth, the 2 events are no longer simultaneous. How do we resolve this paradox? We abandon absolute time. In this situation, the rear of the ship is slightly in the future relative to the middle, and the front is slightly in the past. Yet there is one quantity everyone agrees on. If all observers calculate time squared minus distance squared, they all get the same result.
This is the space-time interval. It is invariant. It does not depend on your point of view. And invariants are the deepest truths of nature.
Because nature does not care about our point of view, we must describe it using invariants. Whenever we discover an invariant, we uncover something truly objective about the universe. Dozens of physicists, including Nobel laureates, call the space-time interval one of the greatest equations in physics, perhaps in all of science, because invariants are fundamental. And the word fundamental matters. It means this is how the universe is built. There is no deeper explanation. The interval is what we call the distance between two events, not a distance in space, but a distance in space-time. So what is an event? It is something that happens somewhere at some time. A finger snap, here, now. Relativity is the study of relationships between events, how far apart they are, and whether they can influence one another. This is how we naturally think about life. Let's meet tomorrow evening at the pub. List the moments of your life, your first day at school, a holiday with your grandmother, a night out with friends. Thread them like beads on a string, and you get your world line, your personal path through space-time. All the moments of your life, past and future, exist somewhere in space-time. Your memories are events that are still there. Your future, including your death, already lies along that line. If you had a perfect stopwatch starting at birth, it would measure the length of your world line. That length is your age. How wonderful it would be to move freely along it, to return to any moment. But the space-time interval forbids this. Here's why. Light from a candle spreads in all directions, forming a growing bubble of light. Slice this bubble in 2 dimensions and it becomes an expanding circle. Stack these circles in time and you get a cone, widening from the past into the future. This is a light cone. Its sides are tilted at 45 degrees because the speed of light is constant. In 1 year, light always travels 1 light year. No matter what path you choose, you can never leave your light cone. Now imagine a distant supernova. It can affect you only when its light cone reaches Earth. Before that moment, no information about the explosion can arrive. Nothing moves faster than light. So causality is limited by the speed of light. But light cones reveal something even deeper, the true difference between space and time. In space, you can move in any direction, turn around, even form loops. In time, everything is forced in one direction, from past to future. You cannot turn back because you are trapped inside your light cone. This lets us define time precisely. Time is the direction in which light cones point. It is the direction in which all allowed paths lead, and where your future inevitably lies. Space is everything perpendicular to that direction. In empty space, without gravity, space-time forms a neat, straight grid. All light cones line up the same way, and time can be defined globally. This is the realm of special relativity. But general relativity adds one final, devastating idea. Space-time is not flat. It has a geometry, and that geometry can bend. Matter and energy bend space-time around them. Objects do not move because of a gravitational force. In Einstein's picture, there is no force at all. Gravity is geometry. To understand curved space-time, imagine a 2-dimensional world. The flatlanders crawl on a surface, forward and back, left and right, but never up or down. Their flat eyes see only flat things. Imagine a reaction if a famous physicist, Flat Albert, stood up and said, "There is another dimension, a direction we cannot point to." Suppose Flat Albert is right. The Flatlanders live on the surface of a table. The 3rd dimension, upward, is real, but invisible to them. They encounter forbidden regions. They must walk around coffee cups, lamps, and books. How did Flat Albert deduce a hidden dimension? "It's the changing patterns of light and dark," he said. "I know what they are. They are shadows." Using mathematics, he realized that shadows are two-dimensional projections of three-dimensional objects. The analogy is perfect. The space-time interval, the thing that does not change with perspective, lives in four dimensions. Distances in space and differences in time are just shadows. We cannot imagine four dimensions, just as Flat Albert could not imagine a coffee cup. But that did not stop him from discovering the true three-dimensional world. Now imagine the Flatlanders believe their table is perfectly flat. But if it is slightly curved, their measurements will reveal strange results. Triangles whose angles do not add up to 180 degrees. Parallel lines that slowly meet or drift apart. That is what we mean by curved space. General relativity tells us how matter and energy curve space-time in their neighborhood. Professional physicists are no better than you at visualizing this. When it comes to four dimensions, we are all Flat Alberts staring at shadows. Fortunately, to understand black holes, we only need to track the behavior of light cones. Physicists invented a beautiful way to do this: Penrose diagrams. General relativity is often called beautiful. Not because of the mathematics, it is brutal. There is a famous joke about Arthur Eddington. When told he was one of only 3 people in the world who understood Einstein's theory, he paused and said, "I'm trying to remember who the third one is." The beauty lies in the ideas. John Wheeler captured it in a single sentence. Space-time tells matter how to move. Matter tells space-time how to curve. The hardest part of general relativity is calculating the curvature of space-time. Black holes are one of the few cases where we can compute the geometry exactly. But how do you draw curved four-dimensional space-time on a flat page? We face the same problem as mapmakers. In 1569, Gerardus Mercator invented a projection to draw the spherical Earth on a flat map. It preserves angles, letting sailors plot straight courses. The price is distortion. On a Mercator map, Greenland looks as large as Africa, even though in reality it is 14 times smaller. Near the poles of a Mercator map, distortion becomes infinite. The poles themselves cannot be drawn at all. Roger Penrose found an elegant way to bring infinity into a finite region of the page. Imagine you are a painter, but instead of canvas, you use space-time. And instead of a brush, you use gravity. That was Penrose's way of thinking. He wanted to draw not just the universe, but its entire infinity on a single sheet of paper. And he succeeded. He created a diagram in which the whole history of the universe fits into the palm of your hand. His trick was simple in spirit. What if we compress infinity without destroying the geometry of light? Penrose used a mathematical transformation that shrinks infinitely distant events while preserving the angles of light rays. The Penrose diagram of flat spacetime is a diamond. All of infinite space and all of time, from the beginning to the end, fit inside this finite shape. The distortion is huge, but chosen very carefully. Like the Mercator projection, it is conformal. It preserves angles. So light rays always travel at 45 degrees, and light cones everywhere point straight up. This makes causality easy to see. Now consider a massive object, say the Earth. Drop an apple and it falls. Gravity pulls not only matter, but light itself. If the apple emits expanding bubbles of light, those bubbles will also bend downward. Near a massive body, light cones are no longer parallel. They tilt more and more under gravity. In other words, time itself bends toward the center of the planet. The apple falls not because a force pulls it, but because its future points downward. Mass reshapes the geometry of the universe. Space and time become relative, their orientation depending on where you are. This is general relativity.
Now imagine how light cones behave inside something far more extreme, a black hole. Person A lights a candle. Its light spreads outward in all directions, forming an expanding light bubble. Person B sees the flash only when the bubble reaches him, when he enters its light cone. Once inside, he cannot escape, because that would require moving faster than light. The surface of a star also emits such light bubbles, but if the star collapses inward, it can become so compact that gravity drags the fabric of space inward at the speed of light. At a certain moment, the star emits its final light bubble. It tries to expand, but space-time itself is falling inward just as fast. The light cone freezes in place. Anything that crosses it can never leave. That frozen light bubble is what we call a black hole. Black holes are light cones held still by gravity.
Take a two-dimensional slice of space. A black hole appears as a frozen circle, forming a cylinder through space-time. Its boundary is the event horizon. Above the horizon, some light can still escape. Below it, all light is trapped. Inside a black hole, light cones force every object inward. Time itself points toward the center. To understand a black hole, we must compare two perspectives: the astronaut who falls in and the distant observer who stays far away. For the distant observer, gravity is weak and space-time appears nearly flat. Time flows calmly from left to right. The horizon looks stationary, a straight vertical line from past to future. Now switch to the falling astronaut. As the horizon approaches, space and time tilt more and more. When the astronaut reaches the horizon, nothing dramatic happens locally, but here, space and time lean at 45 degrees. For the astronaut, the horizon is no longer horizontal, it becomes diagonal, like the surface of a light cone. While the distant observer sees the black hole is frozen, the falling astronaut experiences the horizon as a light cone boundary from which escape is impossible. Crossing the horizon, space and time exchange roles. Time now points downward. The horizon is no longer a place in space, but an event in your past. The center of the black hole is no longer a location, it is an unavoidable event in your future. When a massive star collapses, it emits a final burst of light, a bubble that tries to expand but becomes frozen in curved spacetime. That frozen light cone is the black hole. If we straighten the diagram, global time once again flows left to right. The horizon clearly forms a light cone from which escape is impossible. Once you cross it, the outside universe is gone forever. You can move only toward the singularity, where curvature becomes so extreme that our physical theories collapse. This compact picture is the Penrose diagram of a black hole. The exterior and interior are forever separated. Now that we understand light cones inside black holes, what happens near their edges? What is it like to exist close to one? Remember Miller's planet from the film Interstellar, based on the work of Nobel laureate Kip Thorne? Miller's planet orbits just outside the black hole Gargantua. 5 seconds on its surface correspond to years on Earth. According to relativity, time slows down in strong gravity. Near massive objects, clocks tick more slowly. But gravity is not the only thing that warps time. Special relativity tells us that motion slows time as well. Climb a staircase. You move slightly farther from Earth, so gravity should make your clock tick faster. But you are also moving, so motion makes it tick slower. The two effects cancel. Now imagine two people. Person A floats near a massive object. Person B drifts far away in empty space. A shines a green laser toward B. That beam is a wave of light with 600 trillion oscillations per second. But light is also energy. As the beam climbs out of the gravitational field, it loses energy. Its frequency drops. When it finally reaches B, instead of 600 trillion oscillations per second, only, say, 10 billion remain. Green light has become microwaves. This is gravitational redshift. But where did the missing oscillations go? They didn't disappear. Person A emits 600 trillion oscillations each second. Person B receives only 10 billion per second. There is only one explanation. A second for one person is not a second for the other. It takes person A 1 second to create 600 trillion oscillations, but it takes person B almost 60,000 seconds, nearly a full day, to receive the same number. Their clocks are running at different speeds, and not just mechanical clocks, biological ones too. Heartbeats, breathing, brain activity. Person A inhales, exhales, everything feels normal. But person B watches through a telescope and sees life unfolding in extreme slow motion. Days pass between breaths. Now return to Interstellar. Relativity tells us the stronger the acceleration, the slower you move through time. On Earth, gravity is gentle. Time slows by only a few microseconds per day. On the surface of a neutron star, time slows by hours per day. And at the event horizon of a black hole, time stops. Gravity there is so monstrous that nothing can escape, not even light. On Miller's planet, time flows far more slowly than on Earth because the gravity of Gargantua is 1 billion times stronger than the Sun's. When the crew lands, the soundtrack begins to tick like a clock. 1 second on Miller's planet equals 1 entire day on Earth, about 61,400 seconds for every second they experience. In reality, time flows differently everywhere in the universe. A simple example is the International Space Station. Clocks on board tick slightly slower than clocks on Earth, and we constantly correct them using Einstein's equations. But there is another way to travel through time: speed. Space is vast. There is no limit to how far you can go. The Andromeda Galaxy is 2.5 million light-years away. On a ship moving at 99.9999999% of the speed of light, a round trip would take you only 18 years. But on Earth, 5 million years would pass. So what is the connection between acceleration and gravity? Look up at the sky. Astronauts float aboard the ISS. A dropped screwdriver hangs beside them. Water drifts as trembling spheres. Why? They are not outside Earth's gravity. The station orbits only 400 kilometers above the surface, barely higher than a passenger jet. The ISS is falling toward Earth, just as you would fall from an airplane. But it moves so fast sideways that it constantly misses the planet. This is free fall. And free fall is indistinguishable from floating in deep space. If you were sealed inside a windowless spacecraft, you could not tell whether you were in a gravitational field. Your body and all nearby objects would drift calmly because no force disturbs them. Einstein called this the happiest thought of his life. Gravity can be simulated by acceleration, and gravity itself can be canceled by falling. If your ship accelerates upward with Earth's gravity, you feel at home. You can sit, walk, pour coffee. Without windows, you cannot distinguish the ship from a room on Earth. Reduce the thrust to 1/3, and you are suddenly on Mars. No other force in nature behaves this way. You cannot imitate electricity or magnetism with motion, but gravity can be replaced by acceleration. This idea is called the principle of equivalence. It opened the door to a completely new understanding of reality, one that leads directly to black holes in the most extreme geometry in the universe. In 1916, only 5 months before his death, the astrophysicist Carl Schwarzschild made a stunning discovery. While serving in the German army and calculating artillery trajectories, he found the first exact solution to Einstein's new equations. Einstein had published his theory only weeks earlier. Schwarzschild derived the solution almost instantly and mailed it to him. Einstein replied, "I read your paper with the greatest interest. I did not expect that one could formulate an exact solution so simply." Schwarzschild described the geometry of space-time around a star. Remember Wheeler's maxim? Space-time tells matter how to move. Matter tells space-time how to curve. Schwarzschild told us exactly how space-time curves. Think of Earth. You cannot use the Pythagorean theorem to measure the distance from Buenos Aires to Shanghai. Place a straight ruler 19,600 kilometers long in Argentina, and its far end will miss China. It will hang in empty space. The ruler is straight, the Earth is not. But you can lay down millions of small rulers following the curved surface of the planet. By stitching together flat pieces, you measure distance on a curved world. A perfect example is the Montreal biosphere. From far away, it looks like a smooth sphere. Up close, you see it is made of countless flat triangles stitched together at tiny angles. Any geometry can be built this way. What matters is how the pieces are assembled. In general relativity, curved spacetime is built the same way, by stitching together countless tiny pieces of flat spacetime. Schwarzschild's solution tells us exactly how those pieces are stitched near a star. Einstein remembered this insight as the happiest thought of his life. Gravity can be replaced by falling. If gravity disappears for a freely falling observer, then spacetime must be locally flat around them. Gravity does not arise from a pulling force between objects. It appears because neighboring pieces of spacetime are tilted relative to one another near massive bodies. For the Sun, this effect is tiny. At its surface, clocks fall behind by about 1 minute per year. But near a black hole, everything becomes dramatic. Schwarzschild's solution does not only describe space around a star, add enough mass, and it describes a black hole. The Schwarzschild black hole is the simplest possible model, a non-rotating, perfectly spherical black hole with no electric charge. It has only one parameter: mass. From it, we calculate the size of the event horizon, the Schwarzschild radius. But the universe is not filled with static, perfect spheres. Most objects spin. How do we describe rotating black holes? For that discovery, physics had to wait 50 years. Now return to Penrose diagrams. They compress infinities onto a finite page. Each edge and corner represents a different type of infinity. Here is the puzzle. Look at the Penrose diagram of an eternal Schwarzschild black hole. Its left boundary is not at infinity. It lies at a finite coordinate, r equals 1. This boundary is the event horizon. So far, we have only considered the upper half of this edge, the part we crossed when we fell into the hole. But what lies below? Nothing inside the diamond can cross this boundary, yet since it is not infinite, perhaps something exists beyond it. In 1935, Albert Einstein and Nathan Rosen realized that it does. Studying the mathematics of black holes, they saw they had described only half of the solution. The full picture was far stranger. They wrote, "Four-dimensional space is described mathematically by two sheets which are connected by a hypersurface. We call this connection between the two sheets a bridge." It turned out that a Schwarzschild black hole is not just a cosmic pit, it is a bridge between two universes. Einstein called it a bridge. Today, we call it a wormhole. It turns out we were drawing only half of Schwarzschild's solution. The complete diagram contains not 2, but 4 distinct regions. The first is our universe outside the black hole. The second is the interior, where time ends. But there is a third region, a completely different infinite universe, and a fourth, a white hole.
A white hole is the hypothetical opposite of a black hole. Everything emerges from it, but nothing can ever fall in. It exists in the past, not the future. In this sense, it resembles the Big Bang. A black hole lies in the future of astronauts from both infinite universes. They may choose to jump in or not. A white hole, by contrast, lies in their past. They may receive signals from it, but can never visit it. The two universes are connected by a wormhole inside the black hole. An astronaut from our universe can jump into our black hole. An astronaut from theirs can jump into theirs. They will meet inside, before the singularity destroys them. An observer from Region 1 can enter Region 2, the black hole interior, and encounter another traveler arriving from Region 3. They may even exchange words before reaching the singularity, where time itself ends. This diagram is called the maximally extended Schwarzschild spacetime. The word maximally has a precise meaning. The astronauts we have followed are immortal in principle. Their world lines must be infinitely long unless they hit a singularity. A spacetime is maximally extended when every world line begins and ends either at infinity or at a singularity. But there's a catch. You cannot actually cross the wormhole. Inside a black hole, the coordinate of distance becomes time. Everything is forced towards the singularity, and the wormhole itself evolves. It stretches and tears apart faster than anything could traverse it. Not even light is quick enough. So, the natural question arises, do such exotic objects exist in reality? Eternal Schwarzschild black holes probably do not exist in nature. They are perfectly symmetric and static, so real collapsing stars cannot form them. But Einstein's equations do allow wormholes. In 1988, Kip Thorne and his colleagues studied whether the laws of physics might allow an advanced civilization to build and stabilize a wormhole. Such a wormhole would not form from collapsing stars. Instead, it could be extracted from quantum foam, enlarged to macroscopic size, and stabilized by quantum fields with negative energy density. A wormhole like this would be a time machine, and that possibility is unsettling. Could a being observe Schrödinger's cat alive, travel back through the wormhole, and then kill the cat? The idea still fascinates physicists. Wormholes may be woven into the quantum structure of space-time itself. We will return to this idea. The Kerr solution. In 1963, mathematician Roy Kerr made a breakthrough. He found the exact solution to Einstein's equations for a rotating black hole. It sounds simple, just add rotation to Schwarzschild's 1916 solution. The fact that it took nearly half a century tells you how hard the problem was. Like Schwarzschild's, the Kerr solution describes an eternal black hole. But now the symmetry is broken. Like the Sun and the Earth, a Kerr black hole is flattened at the equator. And that changes everything. A slowly rotating Kerr black hole has three dramatic features. First, the singularity becomes a ring. Only trajectories exactly in the equatorial plane hit it. All others miss. An astronaut can fall into a Kerr black hole and avoid the end of time. Second, there are two event horizons, an outer and an inner one. Third, there is a region outside the outer horizon where space-time is dragged so violently that nothing can remain at rest. This region is called the ergosphere. Imagine you jump toward a Kerr black hole. The first thing you encounter is the ergosphere. Here, standing still is impossible. Space itself whirls like a cosmic vortex. Even light aimed directly outward cannot escape, but you still can. The ergosphere is not the point of no return. Inside it, you are forced to rotate with the black hole. No rocket can stop you. But you could use that rotation to escape, like a surfer riding a wave. Suppose instead you continue inward and cross the outer horizon. Now you have passed the point of no return. You must fall further and cross the inner horizon. And here, the madness begins. Beyond the inner horizon, you regain freedom. The singularity is no longer in your future. You can fly inside the black hole, avoiding the ring singularity. To make all world lines end either at infinity or at a singularity, the space-time must be extended, and the result is shocking. Inside an eternal Kerr black hole, there exists an infinite tower of universes, nested inside one another like Russian dolls. The Penrose diagram would require an infinite sheet of paper. This Kerr wonderland is the only way to remain consistent with general relativity. You can travel from universe to universe, cross the inner horizon, spurt the ring singularity, and emerge through a white hole horizon into a new cosmos. There you find another black hole, dive in again, and the story repeats forever. If you dare to pass through the ring singularity, you may enter an anti-gravity universe, where gravity repels instead of attracts. Even more disturbing, this region allows closed time-like curves, paths that loop through time. In plain words, time travel. These trajectories cannot be drawn on a Penrose diagram because they require motion in a hidden dimension. They begin before your birth and return years later to the same day. This geometry permits them, which means a Kerr black hole is, mathematically, a time machine. This raises terrifying questions. What if you tried to prevent your own birth? It need not be a paradox. The universe might allow time travel and still remain logically consistent.
Stephen Hawking proposed the chronology protection conjecture. The laws of physics must forbid time travel. Most physicists believe that the maximally extended Kerr geometry does not exist in the real universe. Real black holes form from collapsing matter. That matter alters the internal geometry, blocking any portals to other universes. Even worse, an infinite flow of energy along the inner horizon would generate a singularity, sealing the passage completely. Rapidly rotating black holes are even stranger. If the spin becomes too fast, the event horizons disappear. What remains is a naked singularity, a ring of infinite density with no protective horizon. And that is a nightmare for physicists. A naked singularity is a singularity not hidden behind an event horizon. Roger Penrose proposed the cosmic censorship hypothesis, claiming that naked singularities cannot exist in nature, except perhaps the singularity of the Big Bang itself. Why is this so disturbing? Because naked singularities poison space-time with ignorance. The universe becomes hopelessly unpredictable. Even perfect knowledge of the past would no longer determine the future. In 1991, Kip Thorne, John Preskill, and Stephen Hawking made a bet that the laws of physics would prevent naked singularities. In 1997, Hawking lost. Computer simulations succeeded in creating them. He conceded with a caveat: the simulations were highly artificial. Still, they required nothing beyond known physics. The bet was renewed with a new condition: naked singularities would not arise naturally without the intervention of an unimaginably advanced civilization able to fine-tune stellar collapse. Hawking paid his debt by giving Thorne and Preskill t-shirts to clothe the nakedness of the winners. But what prevents a Kerr black hole from spinning itself into a naked singularity? It seems simple. Throw a rapidly rotating star into it, aligned with the black hole's spin. The angular momentum should increase. Yet general relativity gives a shocking answer: the black hole repels the star.
This spin-spin interaction suggests that general relativity is almost designed to preserve cosmic censorship. In natural black holes, singularities always remain hidden behind horizons. So if you were disappointed that nature seems to forbid wormholes and time machines, perhaps you were being too pessimistic. General relativity is extraordinarily rich. It allows a breathtaking variety of spacetimes, and some of that exotic beauty may yet be realized in the universe.
Rotating black holes are not exotic. They exist, and the spacetime around them is described by the Kerr solution. Roger Penrose realized something astonishing. You can extract energy from a rotating black hole. Here is how. Throw an object into the ergosphere and arrange for it to split into two parts. One fragment falls into the black hole, the other escapes. If the geometry is just right, the escaping fragment carries more energy than the original object. How is that possible? Because inside the ergosphere, objects with negative energy can exist. This bizarre fact arises from the exchange of roles between space and time. Emmy Noether showed that energy conservation comes from time symmetry and momentum conservation from space symmetry. When space and time swap roles, energy itself can become negative. If the negative energy fragment falls into the black hole, the hole loses mass and spin. To conserve energy, the escaping fragment must carry extra energy. An advanced civilization could use the Penrose process to dispose of waste and generate power, perfect green energy. But there is a limit. After every Penrose process, the area of the event horizon increases. The black hole slows its rotation. In 1971, Hawking proved that the area of a black hole's horizon can never decrease. He later wrote, "In my scientific career of 45 years, the most thrilling moment was realizing that the exact solution of Einstein's equations discovered by Roy Kerr gives a complete description of the countless massive black holes that inhabit the universe. That awe before beauty, the incredible fact that a discovery born from the search for mathematical elegance finds its exact reflection in nature, convinces me that beauty is what the human mind responds to most deeply." Black holes are the most perfect macroscopic objects in the universe, and because general relativity gives a unique family of solutions to describe them, they are also the simplest. The Schwarzschild and Kerr solutions are profound because they are the only possible geometries of spacetime outside any black hole. Nowhere else in physics does something as complicated as a collapsing star reduce to something so simple and exact. Schwarzschild is defined by one number, mass. Kerr adds a second, spin. With just these two quantities, we can compute the gravitational landscape outside any real black hole. It does not matter what collapsed or how chaotic the process was. Beyond the horizon, space-time becomes perfectly simple. This inspired Subramanian Chandrasekhar to write words that John Wheeler later captured in a famous phrase, "Black holes have no hair." In his memoirs, Wheeler recalled that Feynman accused him of being indecent, but he was only trying to express the astonishing simplicity of black holes. They have no hair. John Wheeler once said that black holes are like a room full of bald people. Hard to tell apart because they show no differences in length, style, or color of hair. And yet, there is something tragic in this beauty. The most precious details of nature seem forever hidden from us. Black holes have horizons, and they appear to condemn us to eternal blindness about whatever falls inside. That blindness is exactly why the Kerr and Schwarzschild solutions work so well. Then Stephen Hawking changed everything with one sentence. Black holes are not completely black. Before 1972, black holes seemed simple. Things fell in, the hole grew, and nothing ever came out.
all traces of what fell inside were lost forever, at least according to general relativity. One day, John Wheeler joked to his student, Jacob Bekenstein, that he felt like a criminal. When he puts hot tea next to cold tea, half an hour later, they're the same temperature. The energy of the world has not changed, but the disorder of the universe has increased. That crime, he said, echoes to the end of time. He was talking about the second law of thermodynamics. In any physical process, the universe becomes more disordered. The quantity that measures disorder is called entropy. Entropy always increases. Then Wheeler asked, "But what if a black hole drifts past and I throw both cups into it? Have I erased my crime forever?" Bekenstein took the question seriously. A few months later, he returned with an answer. A black hole does not hide the crime. Hawking had already proved that the area of a black hole's horizon always increases. Bekenstein realized that this is exactly how entropy behaves. When something falls into a black hole, the horizon area grows, and that growth signals an increase in entropy. The bookkeeping is preserved. The second law is safe. But what is the entropy of a black hole? According to general relativity, a Schwarzschild black hole is defined only by its mass. There are no internal parts to rearrange. So where does its entropy come from? To answer this, we must return to the 19th century. Thermodynamics was founded by practical people. James Joule, a brewer from Salford, wanted to build better steam engines. In the 1840s, Joule built a device where falling weights spun paddles in water. The paddles stirred the liquid and heated it. He proved that heat and mechanical work are different forms of the same thing: energy. Heat is simply the motion of atoms and molecules. When the paddles strike the water, the molecules move faster and the temperature rises. The first law of thermodynamics says energy is conserved. It can change form, but its total amount never changes. This is how a steam engine works. But a steam engine also needs something else: a cold environment. It only works because energy flows from hot to cold, never the other way around. This is the second law of thermodynamics. Your refrigerator does the same thing. It does not create cold from nothing. It pumps heat from inside to outside. That is why the back of your fridge is warm. The link between entropy and disorder was made clear by James Clerk Maxwell. He wrote, "The second law has the same degree of truth as the statement that you cannot recover the same glass of water after throwing it into the sea." Ludwig Boltzmann turned this into mathematics. Entropy, he said, measures our ignorance of the exact microscopic configuration of a system. Before you pour a pot of water into the ocean, you know all the molecules are in the pot. Afterward, you have almost no idea where they are. Entropy has increased. Put simply, entropy is a measure of what we do not know. Then, Claude Shannon revealed the link between entropy and information. Flip one coin. There are two possible states, heads or tails. Call them 0 and 1. You have one bit of information. Flip two coins, 4 states, 2 bits. 3 coins, 8 states, 3 bits. In general, if a system has W possible configurations, the number of bits required to describe it is n equals log base 2 W. Sound familiar? It is the same form as Boltzmann's entropy formula. Entropy tells us about the internal structure of things. It is tightly bound to the amount of information they can store. It is a window into the deepest architecture of reality. Rotating black holes are not exotic. They exist, and the space-time around them is described by the Kerr solution. Roger Penrose realized something astonishing. You can extract energy from a rotating black hole. Here is how. Throw an object into the ergosphere and arrange for it to split into 2 parts. One fragment falls into the black hole, the other escapes. If the geometry is just right, the escaping fragment carries more energy than the original object. How is that possible? Because inside the ergosphere, objects with negative energy can exist. This bizarre fact arises from the exchange of roles between space and time. Emmy Noether showed that energy conservation comes from time symmetry and momentum conservation from space symmetry. When space and time swap roles, energy itself can become negative. If the negative energy fragment falls into the black hole, the hole loses mass and spin. To conserve energy, the escaping fragment must carry extra energy. An advanced civilization could use the Penrose process to dispose of waste and generate power, perfect green energy. But there is a limit. After every Penrose process, the area of the event horizon increases. The black hole slows its rotation. In 1971, Hawking proved that the area of a black hole's horizon can never decrease. He later wrote, "In my scientific career of 45 years, the most thrilling moment was realizing that the exact solution of Einstein's equations discovered by Roy Kerr gives a complete description of the countless massive black holes that inhabit the universe. That awe before beauty, the incredible fact that a discovery born from the search for mathematical elegance finds its exact reflection in nature, convinces me that beauty is what the human mind responds to most deeply." Black holes are the most perfect macroscopic objects in the universe, and because general relativity gives a unique family of solutions to describe them, they are also the simplest. The Schwarzschild and Kerr solutions are profound because they are the only possible geometries of space-time outside any black hole. Nowhere else in physics does something as complicated as a collapsing star reduce to something so simple and exact. Schwarzschild is defined by one number, mass. Kerr adds a second, spin. With just these two quantities, we can compute the gravitational landscape outside any real black hole. It does not matter what collapsed or how chaotic the process was. Beyond the horizon, space-time becomes perfectly simple. This inspired Subramanian Chandrasekhar to write words that John Wheeler later captured in a famous phrase, "Black holes have no hair." In his memoirs, Wheeler recalled that Feynman accused him of being indecent, but he was only trying to express the astonishing simplicity of black holes. They have no hair.
Perhaps we humans of the 21st century are simply unable to perceive the true structure of space-time. When Bekenstein proposed that black holes have entropy, there was one enormous problem. Entropy and temperature always go together. If a black hole has entropy, it must also have a temperature, and anything with temperature must radiate, not only absorb, but everyone knew nothing can escape from a black hole. Then, in 1974, everything changed. Stephen Hawking published his famous paper, "Black holes are not completely black. They glow faintly, like dying embers, very faintly." A black hole with the mass of the Sun has a temperature only a tiny fraction of a degree above absolute zero, millions of times colder than the universe itself. Hawking's discovery triggered a revolution that continues to this day. Quantum theory predicts that a black hole radiates as if it were an ordinary object with a well-defined temperature. The immediate conclusion is staggering. Gravity itself must be a statistical law. Quantum effects inject randomness into the very geometry of spacetime. What this randomness really means remains the holy grail of theoretical physics. In 1973, Bardeen, Carter, and Hawking noticed an eerie similarity between the laws of thermodynamics and the behavior of black holes. Temperature could be replaced by surface gravity, entropy by horizon area. At first, they thought it was just an analogy. Then Hawking realized
it was real. How can something that nothing escapes from shine like a coal? The answer lies in quantum theory. Quantum mechanics describes a world of probabilities. Heisenberg's uncertainty principle says you cannot simultaneously know a particle's position and momentum. This is not ignorance, it is how nature works. The vacuum of empty space is not empty. Particles are ripples in the vacuum sea. Even in perfect darkness, pairs of particles constantly appear and disappear. These are vacuum fluctuations, virtual particles. If we could freeze time and zoom in far enough, we would see them not as ghosts, but as real entities. And near a black hole's horizon, that is exactly what happens. A black hole acts like a magnifying glass, stretching time itself. Virtual particles are born in pairs, one with positive energy, one with negative. Normally, they annihilate instantly. But near the horizon, something extraordinary can occur. The pair is torn apart. The negative energy particle falls into the black hole, reducing its mass. Its partner escapes to the universe as Hawking radiation. The temperature of a black hole is inversely proportional to its mass. Small black holes are hot, large black holes are cold. Hawking's formula unites quantum theory and general relativity. It proves that the mechanics of black holes are thermodynamics in disguise. That equation is now carved on Hawking's gravestone. Black holes are not so black after all. They glow with quantum light, binding thermodynamics, quantum mechanics, and gravity into a single picture. Hawking radiation has three properties that seem mutually contradictory. First, if you fall freely toward the horizon of a large black hole, you encounter nothing at all.
If you try to hover just above the horizon of a large black hole, the acceleration required is so extreme that you are roasted by a torrent of blazing radiation. From far away, that same radiation looks cool and faint. And if you fall freely, you cross the horizon without noticing anything at all. Three descriptions, all true, and yet they seem completely contradictory. Imagine you jump into a black hole. From your perspective, you pass the horizon peacefully. Your doom, spaghettification, awaits only near the singularity. But your friend outside will never see you cross. Instead, they will watch you slow, fade, and finally burn away. General relativity predicts this. Your friend can even lower a thermometer towards you. A thermometer hovering near the horizon experiences violent vacuum fluctuations and becomes immersed in a bath of hot radiation. From that viewpoint, the region around the horizon is a blazing furnace. Your friend concludes that you were incinerated before ever entering the black hole. So what must we abandon? The equivalence principle, the foundation of general relativity, or our quantum description of the vacuum? Either choice would shatter physics. And yet, the paradox has a resolution. It is called black hole complementarity. Both descriptions are correct. From the outside, a black hole is wrapped in a hot, impenetrable atmosphere that vaporizes everything, including you. But from the inside, the horizon is nothing at all. You pass through unharmed. So yes, you can be both spaghettified and evaporated at the same time. There is no contradiction, because the two observers can never compare notes. You cannot tell the outside world that you survived, and the outside observer cannot inform you that you burned. Their records are forever separated. You might object. What if the external observer collects your ashes, then jumps in to show them to you? According to complementarity, that cannot happen. Gathering evidence takes time. By the time the observer crosses the horizon, you have already been torn apart. As strange as it sounds, this appears to be the correct picture. Hawking's original paper was titled Black Hole Explosions. The idea is simple. As a black hole loses mass, its temperature rises. It radiates faster and faster until it shrinks away in a final flash. The process is incredibly slow. A black hole with the mass of the Sun lives for about 10 to the 69 years. Not eternal, but unimaginably long. It may seem that this is irrelevant. After all, who cares about something that takes longer than the age of the universe by 60 orders of magnitude? But if we ignore it, we miss what may be the greatest revolution in physics since Einstein. The revolution began with a single question: do black holes destroy information? Imagine throwing a Bible into a black hole. After an unimaginable time, the black hole evaporates. All that remains is radiation. According to Hawking's calculation, this radiation is perfectly thermal, which means it carries no information at all. So the book is erased from the universe. Every detail of everything that fell in is gone, replaced by a bath of featureless heat. This is the black hole information paradox. In his book, The Black Hole War, Leonard Susskind recalls the moment in 1983 when Hawking first declared that black holes destroy information. Future Nobel laureate Gerard 't stared at the blackboard in silence for a full hour. He was disturbed because all known laws of physics preserve information. If you know the exact state of a system, you can in principle predict its future and reconstruct its past. This is determinism, the idea that the universe is fundamentally predictable. If black holes erase information, determinism collapses. In the distant future, no one could recover the details of the past. Once again, complementarity comes to the rescue. From the outside, nothing ever crosses the horizon. The Bible is burned at the horizon, and its ashes are returned to the universe as Hawking radiation. This is no different than burning a book in a fire. In principle, if you measure every particle in the smoke and ash with infinite precision, a superintelligence could reconstruct the text. The information is not destroyed, only scrambled. From the inside, however, the book is spaghettified near the singularity. We do not know what happens there, but it is the end of time for the book. Both descriptions are true, and they never conflict because no observer can compare them. This forces us to abandon a deeply held belief that an object can exist in only one place at a time. Quantum mechanics already challenges this idea for particles. Complementarity extends the challenge to entire astronauts. You are both evaporated and spaghettified.
Complementarity says that what happens inside the horizon is just as real as what happens outside. The interior of a black hole is somehow the same thing as its exterior. This idea became known as the holographic principle. At first glance, one might imagine a simpler fix. When something falls into a black hole, it is secretly copied. One version falls in, the other is burned and encoded in Hawking radiation. But quantum physics forbids this. The no-cloning theorem states that it is impossible to make an exact copy of an unknown quantum state. Eliminate cloning, and only holography remains. Space-time holography was first proposed by Gerard 't in 1993 and developed a year later by Leonard Susskind. They emphasize that holography must be a universal feature of nature, not just a property of black holes. A hologram in everyday life is a three-dimensional image encoded on a two-dimensional surface. It looks solid. You can walk around it, view it from every angle, and it feels real. A black hole contains the maximum amount of information allowed for its size, and remarkably,
That amount is not measured by volume, but by surface area. This means that for any region of space, all the information inside it is written on its boundary. Tufte and Susskind realized something radical. No region of space can contain more information than fits on its surface.
The most cited paper in all of high-energy physics was written in 1997 by Juan Maldacena. It has been referenced nearly 18,000 times. More than any other work, it reshaped theoretical physics over the past 25 years. It provides the strongest evidence yet that the holographic principle is true. The universe Maldacena studied is not our own, but that is fine. Physicists often work with simplified models. What matters is this: Maldacena did not choose his universe to make holography work. Holography emerged from the mathematics itself. It is easiest to understand his result using a two-dimensional toy universe. The space of this universe is not flat, it is hyperbolic. It looks like the Poincaré disk, a projection beloved by the artist M.C. Escher. Just like a Penrose diagram, this projection compresses infinity into a finite circle. Near the edge, everything appears smaller, not because objects shrink, but because space is being squeezed. Now add a third dimension, time. You get a stack of Poincaré disks, one above the other, like a tall cylinder or a tin can. Time flows upward. Physicists call this space-time anti-de Sitter space. And here comes the miracle. Maldacena showed that everything happening inside this cylinder can be fully described by events on its surface. You can know absolutely everything about the interior just by looking at the boundary. On the surface of the cylinder lives an ordinary world of quantum particles. They collide, entangle, obey the usual laws of quantum mechanics. But there is no gravity there. Particles simply move on a flat two-dimensional surface. Inside the cylinder, everything changes. There is a full three-dimensional space-time. Gravity exists. Black holes can form and evaporate. It is a genuine gravitational universe, yet every event inside, every particle, every black hole, is exactly encoded in the physics of the boundary. This is the ADS/CFT correspondence. A universe with gravity is mathematically equivalent to a universe without gravity living on its edge. Maldacena's discovery is that these two utterly different worlds describe exactly the same physics. When the boundary is calm and no particles are present, the interior space-time is empty and quiet. But when energetic particles appear on the wall, a black hole forms inside the cylinder. The more energy the boundary particles carry, the more massive the black hole becomes. When those particles scatter and settle down, the black hole evaporates, releasing Hawking radiation. So a stunning picture emerges. What we once believed to be a fundamental force, gravity, turns out to be a holographic projection of simpler quantum processes on the boundary. The interior world, with its black holes, curved spacetime, and gravitational waves, is a hologram of boundary physics. Maldacena proved that a specific theory without gravity is exactly equivalent to a completely different theory with gravity. By writing down the equations that show this perfect correspondence, he gave us the first concrete realization of the holographic principle. And now we face a deep question. What is truly real? Does anything actually exist inside a black hole, or is it merely an illusion created by particles on its boundary? Or is it the other way around? Are the boundary particles the illusion, a mathematical trick to describe the real black hole? Maldacena gave a wise answer. We should not ask which description is the true one. Both are equally real. They are different languages describing the same underlying physics. There is no contradiction between them. That is the true power of the holographic principle. It gives us two distinct yet equally valid ways to understand one reality, which means that our own world may itself be a hologram, because everything we are can be encoded perfectly on a distant boundary. It sounds insane, but the evidence is compelling. Recall the paradox where you are both spaghettified and evaporated. Which description is real? Does the black hole truly exist? Or is it only a hologram created by boundary physics? Or is it the boundary theory that is unreal, a clever way to describe the true black hole? The holographic principle answers. There are two equivalent descriptions of the same world. Everything that is true in one is true in the other. No contradictions arise. A black hole forms, then evaporates, leaving only Hawking particles. The same story can be told as a gas of particles evolving by ordinary quantum mechanics on the boundary, with no gravity at all. Because the correspondence is exact, if information is preserved in the boundary theory, it must also be preserved in the gravitational interior. And the boundary theory is a pure quantum system, so information cannot be destroyed. This is what finally convinced Stephen Hawking to concede his famous bet with Kip Thorne and John Preskill. Information really does escape from black holes. Maldacena answered whether information can get out. It can. But how does it get out? Consider two universes connected by black holes. Their point of contact is called a wormhole. At that junction, the physics of two different universes meets. Amazingly, those laws completely determine everything happening at the bridge. Mathematically, a wormhole is the connection of two universes, and to create it, the universes must be quantum entangled. So what is entanglement? Imagine two gloves, one left, one right. You put them in boxes and send one to the other side of Earth. The moment you open your box and see a right glove, you instantly know the other is left. Quantum particles are like these gloves, except that before you look, each glove is simultaneously left and right. Only when you measure does the system decide, and the distant partner is fixed instantly, even across light years. Einstein called this spooky action at a distance. Now, here is the twist. If the entanglement between two universes disappears, the wormhole collapses. What remains are just two isolated black holes in two separate worlds. Entanglement literally builds the wormhole. In 2006, Shinsei Ryu and Tadashi Takayanagi found a precise formula connecting entanglement in geometry. It says, the entropy of entanglement equals the area of the smallest surface that cuts space-time in two. In simple terms, entanglement is measured by the area of the bridge between two regions. The larger the bridge, the deeper the quantum connection.
To know how strongly two particles feel each other across distance, you only need to compute the smallest surface between them. Its area directly measures their entanglement. If entanglement is zero, its entropy is zero, and there is no wormhole. The two quantum systems are not connected at all. No space links them. But if entanglement exists, a wormhole appears. This idea goes far beyond black holes. In 2010, physicist Mark van Ramsdonk showed a fundamental principle. Entanglement creates space. We can stitch space-times together by entangling degrees of freedom and tear them apart by disentangling them. A purely quantum phenomenon, entanglement, turns out to be the key to the emergence of classical space-time geometry. Here is the picture. Take a sphere with a quantum theory on its boundary. Split the boundary in half. If the two halves are maximally entangled, the interior space is smoothly connected. Reduce the entanglement and the space stretches. Remove the entanglement entirely and the two interiors snap into two isolated bubbles. Geometry is determined by entanglement. and geometry in Einstein's theory is gravity. This led physicists to a daring hypothesis. Any two entangled particles are linked by a tiny quantum wormhole, a microscopic bridge. In this view, gravity is a collective effect of entanglement in quantum fields. You, your home, and the entire universe are an immense ocean of entangled particles. Without entanglement, there would be no space and no time.
Now return to the thread we left unfinished. Maldacena showed that information can escape black holes. But how? Until 2019, no one knew. The breakthrough came from the idea of quantum islands. Two independent groups derived the famous page curve using nothing more than Einstein's gravity in quantum mechanics. They discovered that for an old black hole, part of its interior actually lies outside the horizon. This region is called an island. Amazingly, the page curve can be derived using classical physics. Another hint that Einstein's gravity knows far more about the structure of nature than we once believed. Here is an intuitive picture. Imagine the black hole as a prison. Hawking radiation escapes, while its entangled partner particles seem trapped behind the horizon. Classically, those partners should fall to the center and vanish. But the calculation says otherwise. Inside the black hole, an island forms, a region where the partner particles reconnect with the radiation outside. When entangled partners meet, their contribution to entropy cancels. This means that information begins to flow out of the black hole. At first, when the hole is young, there is no island. But as the hole ages, an island appears. By the time the black hole has fully evaporated, all the information has escaped. The paradox is solved. And this is not some exotic trick. The island emerges directly from the union of Einstein's equations and quantum mechanics. Einstein's own theory tells us how information is preserved in the most extreme environments in the universe. It even hints at something bolder. Perhaps the singularity itself is replaced by a quantum network of wormholes leading back outside. If this picture is true, we must ask, does the end of time really await an astronaut falling into a black hole? Now imagine that astronaut is you.
You cross the horizon without resistance and encounter what? A tangled network of wormholes. Tidal forces tear you apart. Everything is scrambled, and the information that once was you leaks back to the universe through those quantum bridges, imprinted in Hawking radiation. These discoveries paint a radical new picture. Space is not fundamental. It emerges from quantum entanglement. Black holes are not prisons for information, but intricate quantum computers, processing and returning information through holographic links between inside and outside. We live in a world where the boundary between inside and outside, between here and there, even between now and then, blurs at the deepest level. Quantum islands reveal that reality is far more interconnected than we ever imagined. John Archibald Wheeler once wrote, "At the deepest foundation of every physical phenomenon lies an immaterial source and explanation. What we call reality arises from asking yes-no questions and recording the answers given by the apparatus. In short, everything physical is information, and we live in a participatory universe." And he added, "Everything is connected to everything." Those words now seem prophetic. Entanglement tracks information escaping black holes. Entanglement creates space, and the way it does so is astonishingly robust. Thankfully so, because we would not want to live in a universe where space could simply fall apart. And here is the surprising twist. Entanglement is also a powerful technology. It is the central resource behind quantum computers. At first glance, Computers seem unrelated to the birth of space, but in a quantum computer, entanglement is the primary way information is encoded. Modern quantum computers, our networks have roughly 100 entangled qubits. Their potential is immense because the space in which computation occurs grows exponentially with each added qubit. These 100-qubit machines can perform calculations in minutes that would take a classical supercomputer longer than the current age of the universe. And their story began with a very practical problem. Quantum information is incredibly fragile.
Quantum information is incredibly fragile. The slightest interaction with the environment can destroy it. So physicists asked a practical question: how do you protect information from noise? The answer turned out to be beautifully simple. Instead of storing information in individual qubits and risking their loss, spread it across the entire system using entanglement. If part of the network breaks, the information survives. A familiar analogy is a QR code. It contains multiple redundant patterns, so even if parts are damaged, the message can still be recovered. But quantum computers cannot make many copies because of the no-cloning theorem. So the trick is to design a quantum circuit that encodes information redundantly without copying and is resistant to environmental noise. In 2015, 4 scientists invented a remarkable code they called HAPPY, named after the initials of their surnames. It was built as a network of pentagons. Each pentagon was a protective unit containing 6 qubits. They were entangled so cleverly that any 3 qubits contained the full information about the other 3. Even if half the qubits were destroyed, the data remained intact. But the real surprise was not the protection, it was the geometry. The pentagons tiled space according to the laws of hyperbolic geometry, exactly like the Poincaré disk. The researchers realized that their code reproduced every feature of the holographic principle. There was a boundary of visible qubits and an interior of hidden ones. All the information about the interior was encoded on the boundary, just like in black hole physics. Even the Ryu-Takayanagi rule appeared. Take a segment of the boundary and draw the shortest path into the interior. The entanglement between that segment and the rest of the boundary equals the number of links crossed. This was no coincidence. The HAPPY code revealed a secret foundation of space itself. Think about it. In the HAPPY code, there is no space at all, only qubits and connections between them. And yet, from the pattern of those connections, geometry emerges. Distance becomes nothing more than the number of links you must cross to get from one point to another. Now scientists believe that real space may work the same way. Space is not fundamental. It arises from a deeper reality, a web of quantum entanglement. At the deepest level, there may be no points, lines, or surfaces, only a network of quantum links far smaller than any particle we can detect. What we perceive is only the large-scale pattern, the smooth space through which we, planets and stars, move. Meters and kilometers are merely ways of counting how many quantum connections separate 2 places. This explains why space is so stable. Information in it is encoded with enormous redundancy. To tear the fabric of space, you would have to destroy an astronomical number of quantum links. And the most astonishing consequence is practical. From studying black holes, we learned how to build quantum computers. And by building quantum computers, we can now simulate black hole physics in the laboratory. 2 fields that once seemed worlds apart have turned out to be 2 sides of the same coin. Nature uses quantum error correction to create stable space. We use the same principles to build quantum machines. We live inside a quantum computer the size of the universe. What we call physical reality may be nothing more than its program running on a vast network of entangled particles. John Wheeler, the visionary physicist of the last century, dreamed of the day when we would understand that everything is made of information.
The happy code suggests that this day may already be here. Does living inside a universe that resembles a gigantic quantum computer mean that we are virtual beings in the simulation of some superintelligence? Probably not. There is no reason to make that leap. Rather, in our search for a quantum theory of gravity, in our most fundamental investigations, we seem to have caught a glimpse of a deeper layer of reality. And understanding that deeper layer may guide us as we design our own quantum machines. Vincent van Gogh once said, "It from bit." Every physical object has an informational origin. Reality arises from answers of yes and no to quantum questions. Now we are beginning to see how. Qubits join into networks. From their connections, geometry emerges. From geometry, gravity. From gravity, the cosmos. History keeps repeating itself. Again and again, we discover techniques that nature has been using all along. It is no surprise that these techniques become our most powerful technologies. Perhaps nature is our greatest teacher. Vincent van Gogh once wrote, "Be clearly aware of the stars and infinity on high. Then life seems almost enchanted after all." By studying black holes, we uncovered a holographic universe, strange, logical, and beautiful in its deep interconnectedness. We stand at the threshold of new discoveries, a time when abstract theories become working technologies, when the search for eternal questions triggers revolutions in computation, when looking into infinity in the sky helps us understand the reality beneath our feet.